Today in class, we discussed osmolarity and tonicity, and sadly, my microphone was not turned on, which apparently is a bit of a problem. So I'm making you this video. In order to discuss these topics, what we first need to do is talk about diffusion. And it turns out if we look at a molecule that is permeable to the cell membrane, it will move from its high concentration to its low concentration. And this happens without any input of extra energy. However, when we talk about osmolarity, what we're going to talk about is actually the movement of water. And it turns out that water likes to move towards the highest concentration of solute. And basically what water's trying to do is I always think of it like an egotistical molecule. It wants to dilute that solute. So in this case, what would happen is the water would move the opposite direction of the solute. However, this is a permeable solute. So if we were to leave it for a long period of time, what we would find is that the permeable solute would start to reach its equilibrium. And while water would initially move toward the highest concentration of solute, eventually, once equilibrium is reached, water will also reach equilibrium. So there's no net movement of water in the case of osmolarity. So then what happens if we've got non-permeable solutes in the equation? Now, this actually becomes interesting. Remember, non-permeable solutes want to go from high to low concentration, but they can't. They can't make it through the cell membrane. And what this means is that in this case, the water will still move toward the highest concentration of solute, but it's never going to move back because the solutes are never going to move. And if this was a closed system, and a closed system would have to be like in a vacuum or something, what we would actually end up with is more water on the side with higher solute than the side with lower solute because of all the water that would be rushing in to try to balance out the concentration. Where we have non-permeable solutes are referred to specifically in terms of tonicity. So osmolarity relates to all the solutes present, and tonicity specifically just the non-permeables, and it's because of this movement of Physiologically, this movement of water is important when we consider something along the lines of a red blood cell. You can imagine that if we were to take that cell and we were to place it into a hypertonic solution, this is a solution that has more non-permeable particles outside than inside, then the water would rush out, and this would very, very quickly cause the cell to shrivel up. If we go on the other side and instead place the cell in a hypotonic solution, this is a solution that has fewer non-permeables outside than inside, now what happens is the water rushes in. And since the water is rushing in to dilute those non-permeables inside, the cell actually swells and could even explode. So physiologically, this is actually very relevant, and it's something that could even lead to death, or it influences your cells when you're dehydrated. They end up very hypertonic. And talk about osmolarity. We talk about osmolytes. These are the number of particles that are in the solution. And these particles can be in two flavors. They can be permeable and non-permeable. So it's the total number of particles. Instead, when we talk about tonicity, we are only referring to the non-permeable particles that are within the solution. So now let's run through some practice problems. If we've got a cell and we have a larger number of particles on the outside than on the inside, in this case, what would you call that? And if you're thinking that the cell is in a hyperosmotic solution, you're correct here. Now, notice I didn't tell you if the particles were permeable or non-permeable. You don't know, but the term hyperosmotic applies here. You don't know about the tonicity. Now, if we make them non-permeable particles, then we can also call the solution hypertonic because we know that there are more non-permeables outside than there are inside. Let's move on to a mixed case where you've got permeables and non-permeables together. So in this case, the pink are going to be permeable, and I'm going to add blue particles, and the blue particles are going to be non-permeable. Okay, so in this case, we have more particles total outside, so we're in hyperosmotic solution, but since we have more non-permeables inside, we're actually in a hypotonic solution. And again, that hypotonic is because we have fewer non-permeables outside than inside, and this would influence the water movement. The water would move in while the solutes would also move in to attempt to balance out, the permeables would attempt to balance things out. Now we're going to try another cell. And in this case, again, I'm going to put the non-permeables in blue. And you can see that I have more non-permeables outside than I have inside. So this means that this would be a hypertonic solution relative to the cell. Alternatively, you could call the cell hypotonic relative to the solution. Both ways happen. Again, hyper means more. Tonic is those non-permeables. So now I'm going to add in permeable osmolytes. And as I'm adding in the permeable osmolytes, all right, so if we start to count these, we can actually look at what we have inside and outside. It turns out I have 5 permeable osmolytes on the inside, and I have 2 permeable osmolytes on the outside. If we look at the non-permeables, I have 3 non-permeables on the inside, and I have 4, 5, 6, 7 non-permeables on the outside. Now, in this case, what this means is that I've got 8 osmolytes in and 9 out, which would make it an ever so slightly hyperosmotic environment. However, really and truly, I meant to draw these equal. So this is almost an isoosmotic. If I change this to 6 permeables in, now we've got 9 osmolytes on either side of the membrane, and assuming equal volume, that means that we are in an isoosmotic environment, even though it's hypertonic. An iso, same. Osmotic is the permeability, or the permeables and the non-permeables together. It's all of the osmolytes. Okay, so now let's think of this more in terms of the water movement and exactly what's going to happen. Okay, so I'm adding in my non-permeables first, or my permeables, excuse me, first. And there are more permeables inside than outside, and these permeables are going to want to cross the membrane. They're going to want to go out of the cell because they want to reach equilibrium. Now, there would be no net water movement in this case, but when I start to add in these non-permeables, now I can make it so that there are more non-permeables outside than there are inside the cell. And even though there was no net water movement when we had no non-permeables, now that we've got the non-permeables, we are going to have net water movement toward the higher concentration of non-permeables, so out of the cell. What this means is if we were to leave this cell for a period of time and let it equilibrate, what would happen is that the cell would end up shriveling because all of that water would leave it. And if we were to look at the concentration of molecules inside that poor shriveled cell that's lost its water, we'd find that the non-permeables have not moved because they can't. And the permeables will be they'll have reached equilibrium. They'll have crossed the membrane until they're in equal concentration inside the cell and out.